Right now, as you're watching this, you think you're sitting somewhere. You think there's a specific time on the clock. But what if I told you that space and time might not actually exist? That everything you've ever known about reality could be wrong? I'm talking about one of the biggest secrets in modern physics. Scientists are starting to realize that the universe we see, touch, and live in might just be a projection, like a hologram. The fabric of space and time that Einstein told us about? It might not be real at all. It might be something that just appears when you zoom out far enough. And if that's true, then what the hell is actually going on? But before I explain what's really happening, you need to understand the problem that made scientists question everything in the first place. See, here's the thing. For over 100 years, we've had two incredible theories that explain how the universe works. The first one is Einstein's general relativity. This is the theory that tells us gravity isn't really a force. It's actually the bending of space and time. When you see a planet orbiting a star, it's not being pulled by some invisible string. It's just following the curves in space-time, like a marble rolling around a bowl. And this theory works. It works so well that we use it to predict the movement of planets, explain black holes, and even make your GPS work on your phone. Without accounting for Einstein's equations, your maps would be off by kilometers every single day. Then we have quantum mechanics. This is the theory of the super small. Atoms, electrons, photons, all that stuff. And quantum mechanics tells us that at tiny scales, reality is weird, really weird. Particles don't have definite positions until you look at them. Things can be in two places at once, and particles that are far apart can somehow be connected in ways that seem to break the rules of normal physics. And just like relativity, quantum mechanics works perfectly. We've built computers, lasers, and all kinds of technology based on it. Both theories are tested and proven. But here's the problem. They don't work together. When you try to apply quantum mechanics to gravity, the math explodes. You get infinities. You get nonsense. The equations break down. And when you try to apply Einstein's smooth, continuous space-time to the quantum world, it doesn't fit. Quantum mechanics says everything is jumpy and uncertain. Einstein's theory says space-time is smooth and predictable. So, which one is right? The answer might be neither, or both. Because what scientists are starting to realize is that maybe we've been asking the wrong question. Maybe space-time itself, this thing we think is the foundation of everything, isn't actually fundamental. Maybe it's something that emerges from something deeper. Now, I know what you're thinking. How can space and time not be real? You're sitting somewhere right now. You can look at a clock. But hold on, because the evidence for this is way stronger than you might think. And it all starts with something you probably learned about in school, but never really understood. Let me explain what I mean by emergence. Think about temperature for a second. When you touch a hot cup of coffee, you feel warmth. You can measure it with a thermometer. It feels totally real. But here's the thing. Temperature isn't actually a fundamental property of the universe. If you zoom in on that coffee and look at the individual molecules, none of them have a temperature. They just have speed and energy. Temperature only shows up when you have billions and billions of molecules moving around together. It's an average. It's what emerges when you step back and look at the big picture. Scientists think space and time might work the same way. At the deepest level, the universe might not be made of points in space or moments in time. Those concepts might only appear when you zoom out and look at huge collections of whatever the universe is actually made of. And here's something I never told anyone before. When I first learned about this in college, it messed me up for weeks. I remember sitting in my apartment at 2 a.m., looking at my hands, at the walls around me, and feeling like I was going crazy. Because if space isn't real, then where am I actually? If time isn't real, then when am I? It sounds like philosophy, but it's not. It's physics. And the evidence is so strong that even the most skeptical scientists are starting to take it seriously. So what is the universe actually made of? Well, that's where things get interesting. And the first major clue came from one of the strangest objects in the universe. But before I tell you what that object is, you need to understand why it's so important. Because this discovery didn't just hint that spacetime might be emergent, it proved that information is more fundamental than the space it's stored in. And that completely breaks everything we thought we knew. The object I'm talking about is a black hole. Black holes are these extreme objects where gravity is so strong that not even light can escape. According to Einstein, if you fall into a black hole, you cross this boundary called the event horizon. Once you're past that point, you're done. You can't send any signal back out. You're completely cut off from the rest of the universe. Now, before I explain why black holes are so important to this story, let me tell you something most people don't know. Black holes aren't just theoretical anymore. We've actually detected them. Not just indirectly through their effects on nearby stars, but directly. In 2015, scientists at LIGO detected gravitational waves from two black holes colliding. These are literal ripples in spacetime, exactly as Einstein predicted. And when I say ripples in spacetime, I mean the distance between objects on Earth got longer and shorter by less than the width of a proton as these waves passed through us. Think about that for a second. We built machines sensitive enough to detect spacetime itself vibrating. That's not just impressive engineering, it's proof that spacetime is real in some sense, that it can be disturbed, that it carries waves. But here's the twist. Just because spacetime can ripple doesn't mean it's fundamental. Water can ripple too, but water is made of molecules. The waves are real, but they're not the deepest description. And black holes, it turns out, are the key to understanding what spacetime is really made of. Now, back in the 1970s, a physicist named Stephen Hawking discovered something wild. He realized that black holes aren't completely black. They actually emit a faint glow of radiation. This happens because of quantum effects near the event horizon. And if a black hole is radiating energy, that means it's losing mass. Over an incredibly long time, a black hole can actually evaporate completely. But here's where it gets weird. When you calculate the entropy of a black hole, which is basically a measure of how much information it contains, you find something strange. The entropy isn't related to the volume of the black hole. It's related to the surface area of the event horizon. Think about that for a second. Imagine you have a box. Normally, the amount of stuff you can fit in the box depends on how much space is inside it, the volume. But with black holes, it's like the amount of information is written on the surface of the box, not inside it. Let me give you a real example of how crazy this is. In 2019, scientists took the first ever picture of a black hole. It's the one you've probably seen, that orange ring around a dark circle. That black hole is in a galaxy called M87, and it's absolutely massive, about 6.5 billion times the mass of our own sun. The event horizon is about 40 billion kilometers across. Now here's what's insane. All the information about everything that ever fell into that black hole, all the stars, all the gas, all the matter from billions of years, isn't stored in that enormous volume of space inside the horizon. According to the math, it's all encoded on the surface, on that two-dimensional boundary. It's like taking a 1,000-page book and somehow writing all the information from every page onto the front cover. And the front cover doesn't get any thicker. The information is just encoded in a different way. But wait, it gets even stranger. When Hawking discovered that black holes radiate, he created what's called the information paradox. See, in quantum mechanics, information is supposed to be conserved. It can be scrambled, it can be hidden, but it can never be destroyed. But if a black hole evaporates completely and disappears, where does all that information go? For decades, this was one of the biggest unsolved problems in physics. Some people thought the information was destroyed, which would break quantum mechanics. Others thought it escaped somehow in the Hawking radiation, but nobody could figure out how. The radiation appeared to be completely random, with no information in it. Then, in the last few years, physicists started to make progress on this, and the answer they're finding is mind-blowing. The information doesn't stay inside the black hole, and it doesn't get destroyed. It gets encoded in the correlations between particles in the Hawking radiation. The radiation isn't actually random, it's incredibly scrambled, but the information is there if you could measure it precisely enough. And here's the key part. To understand how this works, physicists had to use the holographic principle. They had to treat the event horizon as a two-dimensional surface that encodes all the information about the three-dimensional interior. The black hole's interior, the space inside the event horizon, isn't the fundamental thing. The surface is. This led to an idea called the holographic principle. The idea is that all the information in a three-dimensional region of space can actually be encoded on a two-dimensional surface at the boundary of that region. It's kind of like how a hologram works. A hologram is a flat piece of film, but when you shine light on it, it creates a three-dimensional image. The 3D image isn't really there, it's a projection from the 2D surface. Scientists think the universe might work the same way. The three-dimensional world we live in, with all its depth and space, might actually be a projection from information stored on some kind of boundary. Space itself might be a hologram. Now, this isn't just some wild speculation. There are actual mathematical models where this works. In the late 1990s, a physicist named Juan Maldacena discovered a precise mathematical relationship between two different theories. On one side, you have a theory of gravity in a universe with a certain geometry. On the other side, you have a quantum theory without gravity that lives on the boundary of that universe in one fewer dimension. And here's the kicker. These two theories are completely equivalent. Every single thing that happens in the gravity theory can be translated into the quantum theory on the boundary and vice versa. It's like having two different languages that describe the exact same reality. This was huge. It showed that at least in some cases, a universe with space, time, and gravity can be fully described by a theory that doesn't include space at all. The whole extra dimension of space just emerges from the quantum description on the boundary. So if an entire dimension of space can emerge from a quantum theory without space, what happens to the other dimensions of space? Are all three dimensions of space that we experience emergent? And if they are, what happens to the concept of distance? Because what I'm about to tell you will make you question every measurement you've ever made. So if space can emerge, what is it emerging from? A lot of scientists think the answer is quantum entanglement. Entanglement is this bizarre feature of quantum mechanics where two particles can be connected in such a way that measuring one instantly affects the other, even if they're on opposite sides of the universe. Einstein called it spooky action at a distance because he didn't like it. But it's real. We've tested it over and over again. Now, here's where it gets really interesting. Some physicists have found that the amount and pattern of entanglement between different parts of a quantum system seems to determine the geometry of the space that emerges. If two regions are highly entangled, they act like they're close together in space. If they're not very entangled, they act like they're far apart. In other words, distance might not be a fundamental thing. Distance might just be a way of describing how connected different parts of the universe are at the quantum level. Space becomes a map of relationships, not a container that things sit inside. Let me give you an analogy that might help. Imagine you're looking at a social network. You have friends all over the world. Some of them you talk to every day, some you haven't spoken to in years. If you drew a map based on geography, your close friends might be scattered everywhere. But if you drew a map based on how connected you are, how much you interact, your close friends would be near you and the distant ones would be far away. That second map doesn't care about physical location. It only cares about the strength of the connection. Scientists think space might work like that. The geometry of the universe might be a map of quantum connections, not a fundamental grid that exists on its own. But here's where this gets really visual and weird. Imagine reality as an enormous spider web. Each thread in the web is a quantum connection, an entanglement between two parts of the universe. Where lots of threads come together, where the web is dense and thick, that's what we perceive as a region of space. The threads themselves aren't in space, they are space. Or rather, they're what space is made of. Now imagine you're a tiny spider walking on this web. From your perspective, you move from one point to another by following the threads. The distance between 2 points is just how many threads you have to cross to get there. But the threads themselves, the web itself, doesn't exist in some bigger space. It's all there is. The web creates its own geometry from its pattern of connections. That's what the universe might be like, except instead of silk threads, it's quantum entanglement, and instead of a spider, it's you. You're not moving through space, you're moving through a network of quantum connections that creates the illusion of space. And here's something I only recently started to understand, and honestly, it still keeps me up at night sometimes. If this is true, then the distance between you and someone you love, maybe someone on the other side of the planet, isn't really what you think it is. At the deepest level, you're not separated by kilometers or miles. You're separated by the pattern of quantum correlations between the particles that make up your bodies. In a weird sense, distance is just a measure of how much information you don't share. There's actually an experiment that demonstrates something related to this. In 2017, Chinese scientists used a satellite to create entangled photons and send them to 2 ground stations that were over 1,200 kilometers apart. Then they measured the photons and confirmed that they were still entangled. The measurement of one instantly correlated with the measurement of the other. Now, no information traveled faster than light, that's still impossible, but the connection, the correlation, was there. And according to some interpretations of quantum mechanics, the entanglement between those photons is more fundamental than the space separating them. The space is what emerges when you have lots of quantum systems that aren't entangled with each other. It's the lack of connection that creates distance. Think about what this means for a second. You and I, right now, are made of particles. Electrons, quarks, photons. These particles are quantum systems, and some of them might be entangled with particles in other places, other people, other objects. At the deepest level, we're not really separated by space. We're separated by how much entangled we are, or rather, how not entangled we are. If you could somehow measure all the entanglement between all the particles in your body and all the particles in someone else's body, you'd get a number. And that number, in some sense, is a more fundamental measure of your separation than the physical distance between you. The physical distance is just what emerges when you average over billions and billions of quantum connections. Here's another way to think about it. Imagine you have a huge social network graph, like Facebook or Twitter, but way bigger. Everyone who's ever lived is a node in this graph, and the connections between nodes represent relationships. How much you talk to someone, how much you influence them, how much you share with them. Now, you could draw this graph geographically, put everyone at their physical location on Earth. But you could also draw it based on connection strength. People who are strongly connected appear close together in the graph, even if they're physically far apart. People who have no connection appear far apart, even if they live on the same street. Scientists think space might work like that second graph. The fundamental structure is the network of connections. The spatial arrangement we perceive is just one way of visualizing that network. And at small enough scales or in extreme enough conditions, the two ways of organizing things stop matching up. You can have points that are close in the connection sense, but far in the spatial sense. This has actually been tested, in a way. There are experiments with quantum entanglement where particles behave as if they're connected even when separated by large distances. The usual explanation is that they're connected through some non-local quantum correlation. But another way to think about it is that they're actually close to each other in the fundamental information geometry, even though they appear far apart in the emergent spatial geometry we perceive. And this isn't just theoretical weirdness, this has practical implications. Quantum computers work by creating and manipulating entangled states. They're literally using the fact that entanglement creates a different kind of space, a different kind of connection than ordinary physical proximity. A quantum computer with 100 qubits can explore a space of possibilities that's so large it wouldn't fit in the observable universe if you tried to represent it classically. Where is that space? It's not in our three-dimensional space. It's in the space of quantum correlations, the space that underlies our emergent reality. But if space comes from entanglement, and entanglement is about quantum information, then what about time? because time is even stranger than space. And the way that physicists think time might emerge is going to completely change the way you think about your own memories. And if space is emergent, what about time? Time is even weirder. In our everyday experience, time feels like this river that's always flowing forward. The past is behind us, the future is ahead, and we're riding along in the present. But when you look at the fundamental equations of physics, time doesn't really work that way. In Einstein's relativity, time is woven together with space into this four-dimensional fabric called spacetime, and depending on how fast you're moving or how strong the gravity is around you, time can speed up or slow down. There's no universal clock that everyone agrees on. Your now and my now might be different if we're moving relative to each other. And in quantum mechanics, time is even more slippery. In the equations, time appears as a parameter, something you plug in to describe how a system changes, but it's not treated as a physical thing that the system has. It's more like a backdrop. And when physicists try to write down a quantum description of the entire universe, something even stranger happens. In some of these equations, time doesn't appear at all. The equation just describes a static state. There's no evolution, no change, no flow. It's like the universe just is, frozen in some eternal mathematical structure. So how do we get from that to the flowing sense of time we experience every day? The answer might be that time, like space, is emergent. It might arise from the way different parts of the universe change in relation to each other. Think about a clock. A clock doesn't reveal some fundamental thing called time. It's just a system that changes in a regular, predictable way. You compare the hands on the clock to other events like the sun rising or a meeting starting, and you call that time. What if that's all time is? A way of bookkeeping, a way of tracking how different systems change relative to each other. At the deepest level, there might not be a universal timeline. There might just be correlations. When this system is in state A, that system tends to be in state B. And when this changes, that changes too. We interpret those patterns as the flow of time, but really it's just relationships between things. Let me tell you about something that happened to me a few years ago that made this really hit home. My grandfather passed away, and at the funeral, people kept saying things like, "He's in a better place now," or "His time came." And I remember thinking, what does now even mean? If time is emergent, if it's just correlations between different states of the universe, then in some deep sense, my grandfather's life isn't in the past. It's a pattern in the total state of the universe, and that pattern is still there, encoded in memories, in photographs, in the effects he had on the world. The past doesn't go anywhere. It's not a place that exists somewhere behind us. It's information. It's correlations. It's the fact that the current state of the universe carries traces of earlier states. And the feeling of time flowing forward is just our brains, which are also patterns in this universe, processing those correlations in a particular order. I spent weeks after that funeral thinking about this, reading papers, doing calculations, trying to understand what it really means. And I came to realize something profound. Every moment of my grandfather's life still exists in the quantum state of the universe. The information isn't gone. It's just become incredibly diffuse and scrambled. It's mixed into the larger pattern. In a very literal sense, he became part of everything. The atoms that were in his body are now in the air, in the soil, in plants, in other animals. The photons that bounced off him, that carried his image, are spreading out through space. Some of them will travel for millions of years before hitting anything. The effects he had on people, the changes he made to the world, those propagate forward as causal chains that might never end. In a universe where time is emergent, where it's just the direction that correlations flow, death isn't an ending, it's a transformation. The pattern that was a person becomes part of the larger pattern, and that larger pattern is richer for having included them. This might sound like I'm getting philosophical or spiritual, but I'm not. I'm being completely literal and physical about this. Information is conserved in the universe. The total quantum state always evolves in a way that preserves information. When someone dies, the information that was them doesn't disappear. It just becomes harder and harder to reconstruct as it disperses and entangles with everything else. But here's the thing, that's true for everyone and everything. We're all temporarily coherent patterns in a vast sea of information, and eventually those patterns will dissolve and become something else. But the information, the correlations, the effects we have on the world, those persist. They become part of the fabric. And here's where it connects to entropy. Entropy is this measure of disorder, of how many different ways you can arrange a system's parts while it still looks the same on the outside. And there's this law in physics that says entropy always increases. Things get more mixed up over time. A neat stack of papers gets messy. A hot cup of coffee cools down. The universe as a whole is becoming more disordered. And this increase in entropy gives time its direction. It's why we remember the past but not the future. The past is the direction of lower entropy. The future is the direction of higher entropy. If time is emergent from this spreading of information, then time is the arrow of time. The feeling that time moves forward might just be a consequence of the universe moving toward more probable, higher entropy states. But here's something most people don't understand about entropy. It's not actually about disorder in the everyday sense. It's about information. Specifically, it's about missing information. When entropy increases, what's really happening is that information is spreading out, becoming more diffuse, harder to access. Think about it like this. Imagine you have a drop of ink in a glass of water. At first, the ink is concentrated in one spot. You have very specific information. The ink is here, not there. As time passes, the ink spreads out through the water. Eventually, the water looks uniformly gray. The ink is everywhere and nowhere in particular. Has information been destroyed? No. The ink molecules are still there. Each one is in a specific location, but to know where all of them are, you'd need to measure the position of every single particle. The information has gone from being macroscopic, visible to your naked eye, to being microscopic, requiring precise measurements to access. Entropy is a measure of how much information has become inaccessible. And the second law of thermodynamics, the law that says entropy always increases, is really saying that information naturally becomes more diffuse, more spread out, harder to gather. And if time is emergent from this spreading of information, then time is about forgetting. It's about the universe losing track of its own precise state, not because the information is destroyed, but because it becomes so mixed and scrambled that reconstructing the past becomes impossible in practice. This is why you can't unbreak an egg. It's not that the laws of physics forbid it. At the microscopic level, the laws are perfectly reversible. You could, in principle, take all the molecules of a broken egg and precisely reverse their velocities, and they'd fly back together into an intact egg. But the amount of information you'd need to do that, the precision with which you'd have to measure and control every single particle, is astronomical. The information has become inaccessible. The entropy has increased. Some scientists even think this is connected to entanglement. As systems interact, they become more entangled. Their quantum states get more correlated and more complex, and this growth of entanglement looks a lot like the growth of entropy. If space is built from entanglement, and time is the direction that entanglement grows, then space and time aren't separate things. They're two sides of the same coin. There's actually research being done on this right now. Physicists are studying how entropy and entanglement are related in quantum systems, and they're finding deep connections. In some cases, the formulas for entropy and the formulas for entanglement look almost identical. It's like they're measuring the same thing from different angles. If this is right, then the flow of time, the growth of entropy, and the spreading of entanglement are all the same phenomenon. They're all aspects of how information propagates through the universe. And space and time, the stage on which this all seems to happen, are really just different ways of organizing and describing that flow of information. There's actually a beautiful way to visualize this. Imagine a massive library. Not a regular library, but one where every book is a complete description of the universe at a particular moment. The books aren't arranged by time. They're just all there, sitting on infinite shelves. Now, most of these books are completely random, just noise, but some of them have patterns. Some of them have correlations between pages. And if you line up books that have the right correlations, where each book has traces of the ones before it, you create what looks like a timeline. You're not moving through time, you're reading through a sequence of correlated states. And your consciousness, your sense of self, is a pattern that exists across multiple books, across multiple states. The you that existed yesterday is in one book. The you that you are right now is in another book. And the you that will be tomorrow will be in yet another book. But they're all connected by correlations, by information that flows from one to the next. Time is the order you read the books in, but all the books exist at once in this timeless library that is the quantum state of the universe. So if time is just the direction that entropy increases, and entropy is about information spreading out, then what happens at the beginning of the universe where entropy is lowest? Does time even exist there? And more importantly, if time and space both emerge from something deeper, what about gravity itself? Because the answer to that question is even shockinger. Now, let's talk about gravity, because if space and time are emergent, then what about gravity? In Einstein's theory, gravity is the curvature of space-time. Mass and energy tell space-time how to bend, and that bending tells matter how to move. It's a beautiful geometric picture. But if space-time isn't fundamental, then gravity can't be fundamental either. Some physicists think gravity might be what's called an entropic force. Let me explain what that means. An entropic force is a force that arises because of statistics, not because of some direct push or pull between objects. Here's an example. Imagine you have a long polymer molecule floating in water. The molecule naturally wants to coil up into a ball, but there's no force pulling the ends together. What's happening is that there are way more ways for the molecule to be coiled up than there are for it to be stretched out. The molecule is just exploring different configurations randomly, and it spends most of its time in the configurations that are more probable, which are the coiled ones. From the outside, it looks like there's a force pulling it inward, but really, it's just entropy. Some scientists think gravity works the same way. When you move an object, you're changing how information is distributed in the space around it, and the system naturally evolves toward configurations that have higher entropy. That tendency looks like an attractive force pulling objects together. We call it gravity, but it's not a fundamental interaction. It's an emergent effect, a consequence of the universe moving toward more probable states. This is a radical idea, and not everyone agrees with it, but it fits with the broader picture. If space, time, and gravity are all emergent, then the equations of Einstein's general relativity aren't the deepest description of reality. They're like the equations of fluid dynamics. They work really well for describing water flowing, but they don't tell you that water is made of molecules. They're an effective theory, useful at large scales, but not the final word. Let me give you a really unexpected example of an entropic force that you've definitely experienced but never thought about. Have you ever noticed that when you open a bag of chips or a package of food, it's really hard to get it perfectly flat again? Like, you can press out all the air and fold it down, but it never quite goes back to the way it was. That's an entropic force in action. When the package is unopened, all the air molecules inside are arranged in one very specific configuration. But once you open it, those molecules can explore way more configurations. They spread out into the room, and the number of ways they can be arranged outside the package is astronomically larger than the number of ways they can be arranged inside. So even though there's no force actively pushing them out, they naturally tend to stay out. The package doesn't reseal itself because entropy wants to increase. Now, scale that up, way up, to the entire universe. Every particle, every bit of information is constantly exploring different configurations, and when a massive object like a planet is present, it changes the number of possible configurations in the space around it. The information landscape gets warped, and objects naturally fall toward configurations that have higher entropy. We call that falling gravity, but it might really be entropy. If this is true, and I want to be honest here, I'm not 100% sure it is, but if it's true, then gravity isn't one of the fundamental forces of nature. Electromagnetism is fundamental, the strong nuclear force is fundamental, the weak nuclear force is fundamental. But gravity? Gravity is a side effect. It's what happens when you have space, time, and matter all emerging from the same underlying structure of information and quantum states. This idea actually came from a Dutch physicist named Erik Verlinde back in 2010. He published a paper arguing that gravity is an entropic force, and it caused a huge controversy. Some physicists thought it was brilliant, others thought it was completely wrong, and the debate is still ongoing. The problem is it's really hard to test directly. At everyday scales, whether gravity is fundamental or emergent doesn't matter. The equations work the same way. You'd need to probe extreme conditions, like near black holes or at the Planck scale, to see the difference, and we can't do that yet with current technology. But there are indirect tests. If gravity is emergent, there should be tiny corrections to Einstein's equations in certain situations. Scientists are looking for these corrections in cosmological data, in the motion of galaxies, in gravitational wave signals. So far, nothing conclusive, but the search continues. What's interesting to me is that regardless of whether Verlinde's specific idea is right, the general principle seems sound. If space and time are emergent, then gravity, which is fundamentally about the structure of space-time, must be emergent too. There's no way around it. You can't have an emergent stage with a fundamental actor. They have to emerge together. But this raises a huge question. If gravity is emergent, and if it only appears at large scales, then what happens at the smallest possible scales? What happens when you zoom in so far that space and time themselves break down? Because at that level, something truly bizarre happens, and it's called the Planck scale. So if space, time, and gravity aren't fundamental, what is? A lot of scientists think the answer is information. At the deepest level, the universe might be made of bits of information and rules for how those bits interact and change. Quantum mechanics already has a strong connection to information. Concepts like entanglement, entropy, and measurement are all about what different parts of a system know about each other. If that's true, then particles, fields, space-time, all of it might be emergent patterns in an underlying network of information. Distance becomes a measure of how connected different bits of information are. Time becomes a measure of how information flows and spreads. Gravity becomes the tendency of information to distribute itself in certain ways. From this perspective, the universe isn't a stage with actors on it. The universe is a vast, evolving web of information, and everything we see is a pattern in that web. Now, let me tell you about something even weirder. There's an idea that at the smallest possible scales, space and time might not just be emergent, they might break down completely. There's a length scale called the Planck length. It's absurdly small, about 10 to the minus 35 meters. That's so small that if you made an atom the size of the entire observable universe, the Planck length would be about the size of a tree. At this scale, the effects of both quantum mechanics and gravity are equally strong, and that's where things get messy. At the Planck scale, quantum fluctuations become so intense that space-time itself starts to fluctuate wildly. The smooth fabric Einstein described gets replaced by something chaotic and foamy. Some scientists call it space-time foam. At this scale, the idea of a fixed distance or a precise moment in time doesn't make sense anymore. The geometry itself is uncertain. And there's another problem. To measure something very precisely at these tiny scales, you need a lot of energy. But if you concentrate too much energy in a small region, Einstein's equations say you'll create a black hole. So trying to probe smaller and smaller distances eventually defeats itself. The universe has a built-in limit to how finely you can look. This suggests that space and time as we understand them simply don't exist below the Planck scale. There might be something else there, something more abstract, but it's not space and time in the usual sense. Let me put this in perspective with something really concrete. The Planck length is about 10 to the minus 35 meters. A proton, one of the particles in the nucleus of an atom, is about 10 to the minus 15 meters across. That means a proton is 100 quadrillion times bigger than the Planck length, 20 orders of magnitude bigger. To give you a sense of how big that ratio is, imagine a proton the size of a grain of sand, about a millimeter. If that's your proton, then the Planck length would be about 10 to the minus 23 meters. That's still way smaller than an atom. You'd need to shrink down about 10 million more times to get to an atom-sized scale. Or here's another way to think about it. The entire observable universe is about 10 to the 26th meters across. A human is about 1 to 2 meters tall. The ratio between the universe and a human is about 10 to the 26th. The ratio between a human and the Planck length is about 10 to the 35th. That means you are proportionally closer in size to the entire observable universe than you are to the Planck scale. You are literally closer to the scale of the whole cosmos than to the smallest meaningful unit of length. At that scale, reality is not just different, it's incomprehensible in the language we normally use. And here's something I find absolutely fascinating. The Planck scale isn't just small, it represents a fundamental limit to measurement, a place where all our concepts break down simultaneously. Let me explain what I mean. The Planck length comes from combining three fundamental constants: the speed of light, which sets the maximum speed of information, Planck's constant, which sets the scale of quantum effects, and Newton's gravitational constant, which sets the strength of gravity. When you combine these three numbers in just the right way, you get a length scale where quantum effects and gravitational effects are equally important. Above this scale, you can usually ignore one or the other. When studying atoms, you can ignore gravity because it's so weak. When studying planets, you can ignore quantum mechanics because the objects are so big. But at the Planck scale, you can't ignore either. They're both screaming at you, demanding to be included in the calculation. And when you try to include both, the equations go crazy. This is why physicists are so desperate for a theory of quantum gravity, not just because it would be intellectually satisfying, but because without it, we literally cannot describe what happens at the Planck scale. We have a blind spot in our understanding of reality, a region where our best theories simply stop working. And that blind spot matters, because in the early universe, in the first fraction of a second after the Big Bang, the entire cosmos was Planck scale sized. Everything we see today, all the galaxies, all the stars, all the atoms, all emerged from that Planck scale state. If we can't describe the Planck scale, we can't fully understand where we came from. Similarly, at the center of a black hole, Einstein's equations predict a singularity, a point where the curvature becomes infinite. But most physicists think this is just a sign that the equations are breaking down, that we're hitting the Planck scale again, and need quantum gravity to make sense of what's really there. Different theories propose different ideas about what that something else might be. In loop quantum mechanics, space is made of tiny discrete loops. It's quantized, like energy levels in an atom. There's a smallest possible unit of area and volume. Space isn't continuous, it's grainy, like a digital image made of pixels. In string theory, the fundamental objects aren't points, but tiny vibrating strings. The different vibrations of these strings give rise to different particles. And in some versions of string theory, space-time itself can emerge from the dynamics of these strings and higher dimensional objects called branes. In other approaches, the fundamental structure is a network or a graph. The nodes represent basic units, and the links represent connections. Geometry emerges from the pattern of connections, like how a large enough network of points can look like a smooth surface from far away. All of these approaches share a common theme. They're trying to describe reality without starting from space and time. Instead, space and time are things you derive, things that appear when you look at the deeper structure in the right way. But here's what really gets me. If space and time don't exist at the Planck scale, then what about the Big Bang? What does it even mean for the universe to have a beginning if time doesn't exist at that point? And more importantly, what does all of this mean for you and me, for our everyday experience of reality? So here's the big question. If all of this is true, if space and time really are just emergent patterns, what does that mean for us? On one level, it doesn't change anything. You still wake up in the morning, you still have places to go and things to do. The laws of physics that govern everyday life are still the same. Apples still fall, planets still orbit, your phone still works. But on a deeper level, it changes everything. It means that the reality you experience, the world of objects in space and events in time, is like the surface of an ocean. It's real, it's there, you can interact with it, but underneath there's a whole other structure, a depth that you don't directly perceive. The waves and ripples you see are patterns in that deeper ocean, but the ocean itself is something else entirely. It means that when you look around and see space stretching out in all directions, you're not seeing the fundamental fabric of reality. You're seeing a translation, an interface, a way that a much more abstract structure presents itself to beings like us who are made of many, many particles interacting in regular, stable ways. And it means that the question, "Where are you?" might not have the simple answer you think it does. You're not located at a specific point in a fundamental grid. You're a pattern of information, a collection of correlations and interactions, and the feeling of being located here and now is something that emerges from the way those patterns are organized. This also raises questions about the early universe. In the standard picture, the Big Bang is described as the moment when space and time themselves came into existence. But if space and time aren't fundamental, then the Big Bang might be better understood as a transition, a change from one phase where geometric descriptions don't apply to another phase where they do. It's kind of like water freezing into ice. The molecules are the same before and after. What changes is how they're arranged. In the early universe, the fundamental degrees of freedom, whatever they are, might have been arranged in a way that didn't correspond to anything we'd recognize as space or time. Then, as the universe expanded and cooled, those degrees of freedom settled into a pattern that gave rise to the space-time we see today. And here's something even more mind-bending. If the structure of space is tied to entanglement and information, and if observers are systems that process information, then the role of the observer might be deeper than we thought. An observer isn't just someone passively watching the universe. An observer is a physical system that interacts with other systems, creating correlations, storing information, and, in a sense, participating in the structure that gives rise to space-time itself. This doesn't mean you're creating reality with your mind. It means that as a physical being, you're part of the web of interactions that the universe is made of. The geometry you experience, the flow of time you feel, these are features of how you, as a complex system, relate to the rest of the universe. Let me share something personal here. When I really started to understand this, really let it sink in, I went through this phase where I felt disconnected from everything. If space isn't real, if I'm just a pattern, what does any of it matter? Why does anything I do have meaning? But then I realized something. The fact that space and time are emergent doesn't make them less real. It makes them more beautiful, because it means reality has layers. The everyday world we experience is one layer, and it's completely valid. But underneath, there's this incredible web of quantum connections, this dance of information and entropy that gives rise to everything we see. And we're not separate from that web. We are the web. We're the part of the universe that's complex enough to look back at itself and understand what it is. Every thought you have, every decision you make, every connection you form with another person, all of that is the universe organizing information in new ways. You're not just in the universe, you are the universe experiencing itself. Different observers with different structures and different ways of processing information might carve out slightly different effective descriptions of the same underlying reality. At human scales, these differences are tiny. We all agree on distances, times, and the basic layout of the world. But in principle, the geometry isn't absolute, it's relational. There's also a connection here to the limits of knowledge. If space-time is emergent and tied to information, then there are fundamental limits to what can be known. You can't measure a distance more precisely than the Planck length.
You can't pin down a moment in time more precisely than the Planck time. These aren't just practical limits due to our technology, they're built into the structure of reality itself. This means that the universe has a kind of inherent privacy. There are things that are, in principle, hidden from any observer, and those hidden details might be part of what gives rise to the emergent picture we see. Here's an analogy that might help tie everything together. Think about a video game. When you're playing a video game, you see a character moving through a three-dimensional world. There are buildings, landscapes, other characters. Everything seems to exist in space. But the video game isn't actually made of space. It's made of code. It's made of information stored in the computer's memory. The 3D world you see is a rendering, a translation of that code into something visual that makes sense to you as a player. And here's the thing. The code doesn't care about the 3D layout. Two objects that appear far apart in the game world might be right next to each other in the computer's memory. The distance you see is an interface. It's a way of organizing the information that makes the game playable. The universe might be like that. The three-dimensional space we move through, the time that flows forward, these might be the interface, the rendering. And the actual code of the universe, the deep structure, is this network of quantum states and information that doesn't look anything like space and time. Now, the universe is obviously way more complex than a video game. It's not running on some computer outside of reality. It is reality. But the analogy captures something important. The map is not the territory. The interface is not the code. And space and time might be the interface, not the code. But if that's true, if we're living in an interface, then here's the question that should terrify you. Who or what designed the interface? Or is there no designer at all? Is it just an inevitable consequence of how information organizes itself? And what does it mean for free will if we're patterns in a deterministic web of quantum states?
Now, you might be thinking, this all sounds like wild speculation. Where's the evidence? And that's a fair question, because most of these ideas operate at scales we can't directly probe with current technology. But there are indirect ways to test them, and scientists are working on this right now. One approach is to look for tiny violations of Einstein's equations at very small scales or in extreme environments. If spacetime really breaks down at the Planck scale, there might be subtle effects that show up in things like the cosmic microwave background radiation, which is light from the very early universe. Researchers are analyzing this radiation for patterns that might hint at a discrete or emergent structure of space. Another approach involves studying black holes more carefully. The holographic principle makes specific predictions about how information is stored and how entropy behaves. As we get better at observing black holes and their radiation, we might find evidence that supports or contradicts these ideas. There are also experiments with quantum entanglement. Quantum computers are really good at simulating quantum systems, and some researchers are using them to model simple versions of emergent spacetime. They create networks of qubits, entangle them in specific patterns, and see if something that looks like a geometric space emerges from the math. Early results are promising. And here's something that surprised me when I learned about it. Some scientists are even looking at biological systems for clues. There's this idea that if the universe is fundamentally about information processing, then maybe the way biological brains process information could give us hints about how the universe processes information at a deeper level. It's speculative, but it's the kind of creative thinking that sometimes leads to breakthroughs. The point is, this isn't just philosophy, it's science. People are coming up with ways to test these ideas, even if the tests are hard and the results will take years or decades to come in. But while we're waiting for those experiments, there's one more thing I need to tell you. Because if space and time are emergent, there's one phenomenon that becomes even more mysterious than it already was, and that's consciousness. Because if you're a pattern of information, then what does it mean to be aware? Let's talk about consciousness for a minute, because this is where things get really personal. If you're not located at a point in space, if you're really a pattern in a web of quantum information, then what does it mean to be you? What is consciousness in a universe where space and time aren't fundamental? I don't have all the answers to this. Nobody does. But I can tell you what some physicists and philosophers think. One idea is that consciousness is itself an emergent phenomenon. Just like temperature emerges from molecules and space emerges from entanglement, maybe consciousness emerges from the way information is organized in your brain. Your brain is an incredibly complex system. It has about 86 billion neurons, each connected to thousands of others. The pattern of connections, the way signals flow through the network, creates something that has never existed before in the universe. It creates awareness. It creates the feeling of being you. And if space and time are emergent, if they only exist at certain scales, then maybe consciousness is the same. Maybe it only exists when information is organized in very specific, very complex patterns. And human brains are one of the few places in the universe where that happens. But here's what keeps me up at night. If consciousness emerges from patterns of information, and if those patterns are constantly changing as your brain processes new experiences, then are you really the same person you were yesterday, or 10 years ago? In some deep sense, the you that existed in the past is a different pattern than the you that exists right now. The only thing connecting them is correlation, memory, information that flows from one pattern to the next. And if time is emergent, if it's just the direction that these correlations point, then maybe the whole idea of a continuous self, a you that persists through time, is also emergent. Maybe you're not a single thing that exists through time. Maybe you're a series of patterns, each one carrying information from the last, and the feeling of continuity is just your brain stitching those patterns together into a narrative. I told you this gets personal, because when I think about this, when I really let myself sit with it, it changes how I think about everything, about relationships, about choices, about what matters. If I'm a pattern that will eventually dissolve, if the atoms that make up my body will scatter and become part of other things, if even my memories will fade and be lost, then what's the point? But then I remember, those atoms, that information, doesn't disappear. It just reorganizes. It becomes part of new patterns. And those patterns might be completely different from me, but they're still part of the same web, the same universe. In a very real sense, nothing is ever truly lost. It just changes form. And the connections we make with other people, the love, the experiences, those are also patterns. They're information encoded in multiple systems, spread across multiple brains. When you share a moment with someone, when you create a memory together, you're creating a pattern that exists in both of you. You're entangling your information. And that pattern, that connection, is as real as anything in the universe. Because in a universe where everything is patterns and information, patterns and connections are all there is. Let me tell you about a conversation I had with my best friend a few years ago that really drove this home. We were sitting on a beach at sunset, just talking about life, and he said something I'll never forget. He said, "You know, every conversation we've ever had has changed my brain, literally. The neurons in my head are physically different because of you. You're part of me now." At the time, I thought it was just a nice sentiment. But later, when I really understood this stuff about emergent reality and information, I realized he was right in a deeper way than either of us knew. Every interaction you have with someone physically changes both of your brains. Neurons fire, connections strengthen or weaken, new patterns form. You're quite literally becoming entangled in each other's information. And those changes propagate. Your friend acts differently because of your conversation. They interact with other people differently. Those people are changed, and on and on. Every interaction sends ripples through the information web that is reality. You're constantly reshaping the universe in tiny ways, and the universe is constantly reshaping you. This is what consciousness is in this view. It's not a thing you have, it's a process. It's what happens when information flows through a sufficiently complex system in just the right way. And because you're constantly exchanging information with the world around you, your consciousness isn't really contained inside your skull. It's distributed, it's relational, it's part of a larger pattern that includes other people, the environment, the whole web. Some scientists take this even further. There's an idea called integrated information theory that tries to measure consciousness mathematically. It says that a system is conscious to the degree that it integrates information, that it creates a unified whole that's more than just the sum of its parts. By this measure, a thermostat has a tiny amount of consciousness because it integrates information about temperature. A computer has more because it integrates more information in more complex ways, and a human brain has vastly more because of how incredibly integrated and complex it is. If this theory is right, then consciousness isn't something magical or separate from physics. It's a measure of how much a system is doing what the universe is always doing, organizing information. And here's something wild. If consciousness is about integrated information, and if the entire universe is a vast web of information, then maybe the universe itself, the total pattern, has some form of consciousness. We would be like neurons in its brain, individual patterns contributing to a much larger pattern that we can't fully perceive from our limited perspective. But if the universe is conscious in some sense, if awareness is just information integration, then what happens when we die? Does the pattern that was you really disappear, or does it persist in some form in the total information of the universe? And more importantly, what does it mean to live a meaningful life in a universe where nothing is permanent, but everything is connected?
Let me bring this all together, because I know we've covered a lot. For over a century, we thought space and time were the foundation of reality. Einstein showed us they could bend and stretch, but we still thought they were fundamental. Now we're realizing that might not be true. Space might emerge from quantum entanglement. Time might emerge from the growth of entropy and the flow of information. Gravity might emerge from the statistical behavior of information trying to spread out. And even consciousness might emerge from patterns of integrated information. Everything we thought was fundamental, everything we thought was the bedrock of reality, turns out to be a pattern, an emergent phenomenon, something that appears at certain scales when you look at the universe in certain ways. So, what is fundamental? The honest answer is, we don't know yet. But the best guess, the one that more and more evidence points toward, is that information is fundamental. Quantum information. The universe at its deepest level is not made of stuff. It's made of relationships, correlations, possibilities, and rules for how those things change. Space is how we organize those relationships when there are a lot of them and they're stable. Time is the direction those relationships tend to evolve. Gravity is the tendency of information to spread. Matter is stable patterns in the quantum fields. And consciousness is what happens when a pattern becomes complex enough to model itself and the world around it. This is a completely different picture of reality than the one we started with. It's not a universe of objects in a box. It's a universe of connections in a network. And everything, from the smallest particle to the largest galaxy, to your own thoughts right now, is part of that network. And here's what I think is the most important part. This isn't just abstract theory. This changes how you can think about your place in the universe. You're not a tiny, insignificant speck in a vast, empty void. You're a pattern in the universe's web of information. You're the way the universe has organized itself to be aware of itself in this particular place and time. When you look at the stars, you're not separate from them. You're made of the same atoms, governed by the same laws, part of the same web. The light from those stars travels across space, which isn't really a void, but a network of quantum connections, and enters your eye where it creates patterns in your brain, which are also patterns in the same network. You are the universe looking at itself. And when you connect with another person, when you share an experience or an idea, you're creating new patterns, new entanglements in the web. You're literally changing the structure of reality in a small but real way. Every choice you make, every thought you have ripples through the web. Not in some mystical sense, but in a physical, information-theoretic sense. The pattern that is you influences the patterns around you, which influence other patterns, and so on. In a universe where everything is connected, where nothing exists in isolation, you matter. Not because some external force says so, but because you're part of the fabric. You are the fabric. And that, to me, is more meaningful than any other worldview I've encountered. But there's one more thing, one more implication of all this that I haven't told you yet. And it's about the future, because if space and time are emergent, if reality is fundamentally about information, then what happens when we learn to manipulate that information directly? What kind of technologies might become possible?
Let's talk about what this might mean for the future. Because if these ideas are right, if space and time really are emergent from quantum information, then we might be on the verge of technologies that sound like science fiction. Think about it. If distance is really just a measure of quantum correlation, and if we learn to create and manipulate entanglement on large scales, we might be able to create shortcuts through space. Not in the sense of faster-than-light travel, which still seems impossible, but in the sense of creating highly entangled regions that are close in the emergent geometry, even if they're far apart in the everyday picture. Some physicists have speculated about this. There's this idea that certain types of wormholes, which are tunnels through spacetime, might be mathematically equivalent to entangled particles. If that's true, then creating a traversable wormhole might be a matter of engineering the right pattern of quantum entanglement. We're nowhere near being able to do this. It might not even be possible, but it's not ruled out by the laws of physics as we understand them. Or think about quantum computers. Right now, quantum computers work by creating and manipulating entangled quantum states. They're still in their early stages, but they're already doing things that classical computers can't do efficiently. If we can scale them up, if we can create larger and larger entangled systems, we might be able to simulate not just other quantum systems, but the emergence of space-time itself. Imagine being able to create a tiny universe inside a quantum computer, a universe with its own emergent space and time, its own physical laws. You could run experiments on it, see how it evolves, maybe even see if patterns that look like life or consciousness emerge. It would be the ultimate laboratory for testing theories about the nature of reality. And here's something even wilder. If consciousness really is about integrated information, and if we can measure and manipulate information at the quantum level, we might be able to create artificial consciousness that's not based on biological neurons. Not just AI that acts conscious, but systems that actually are conscious by any reasonable definition. This raises huge ethical questions, obviously, but it also opens up possibilities. If we can understand consciousness as a pattern of information, and we might be able to preserve it, not in the sense of uploading your brain to a computer, which is probably impossible with current approaches, but in the sense of understanding what patterns are essential to you and finding ways to maintain those patterns even as the physical substrate changes. I know this sounds like fantasy, but 50 years ago, the idea of nuclear power sounded like fantasy. 100 years ago, the idea of nuclear power sounded like fantasy. The history of physics is full of things that seemed impossible becoming reality once we understood the underlying principles. And the underlying principle here is profound. If space, time, matter, and even consciousness are all emergent from information, then the universe is far more malleable than we thought. The solid, unchanging laws of nature might be more like software than hardware. At the deepest level, reality is code. And if we learn to read and write that code, we might be able to do things that seem impossible today. But with that power comes responsibility, and that's something I think about a lot. If we really are patterns in the universe's web of information, if our choices ripple through that web and influence the patterns that come after us, then we have a responsibility to create patterns that make the universe better, not worse. To use our understanding not just to manipulate reality for our own benefit, but to help the whole web thrive.
because we're not separate from the web. We are the web. When we damage it, we damage ourselves. When we enrich it, we enrich ourselves. And this brings me to the final question, the one that, honestly, I still don't have a full answer to. If everything is information, if patterns are all there is, then what gives some patterns value and others not? Why should we care about consciousness, about life, about beauty? What makes the universe meaningful? So, we've reached the end of this journey. And I want to talk about meaning. Because here's the thing. When you first learn that space and time might not be fundamental, that you might just be a pattern in a web of information, it can feel nihilistic. It can feel like nothing matters. If you're just a temporary pattern that will eventually dissolve, if the universe will eventually reach maximum entropy and all patterns will fade, what's the point? I struggled with this for a long time, and here's what I've come to believe. Meaning isn't something the universe gives you. It's something you create. And the fact that you're able to create it, the fact that patterns can become complex enough to value other patterns, to care about things, to love and create and wonder, that's the most remarkable thing about the universe. Think about it. The universe started as a nearly uniform sea of energy. No structure, no complexity, just quantum fluctuations in fields. And over billions of years, through the laws of physics, through the growth of entropy and the formation of structures, it organized itself into stars, planets, and eventually, life. And life organized itself into brains, and brains organized themselves into societies, cultures, art, science, philosophy. The universe became aware of itself. It developed the capacity to ask questions about its own nature. And now, through science, we're starting to understand that the very thing asking the question, consciousness, is made of the same stuff as the answer. It's information, organized in a particular way. We are the universe's way of knowing itself. That's not meaningless. That's the opposite of meaningless. That's the most profound thing I can imagine. And the fact that it's temporary doesn't diminish it. In fact, I think it makes it more valuable. Every moment, every experience, every connection you make is unique. It's a pattern that has never existed before and will never exist again in exactly the same way. The specific configuration of quantum states that makes you, right now, is one of an infinite number of possibilities, and it exists for a brief moment in the universe's history. That's precious. That's worth something. And the patterns you create, the ripples you send through the web, they persist. They influence other patterns. The words you speak might change someone's thoughts, which might change their actions, which might change the world in small ways. The love you give might be remembered, might be passed on, might echo through generations. In a universe made of information, every interaction is a form of immortality, because the information doesn't disappear. It just gets mixed into the larger pattern. And in some sense, you become part of everyone and everything you've ever influenced. Let me share one more personal thing, and then I'll wrap this up. A few months ago, I was going through a really difficult time. Personal stuff, nothing to do with physics. And I was lying in bed one night, unable to sleep, and I started thinking about all this, about emergent space-time, about information, about patterns. And I realized something. The pain I was feeling, the emotions, the sense of loss, all of that was also a pattern of neurons firing in my brain. And like all patterns, it was temporary. It would change. It would evolve into something else. The information would reorganize. And that thought strangely gave me comfort. Not because it made the pain less real. The pain was real. It was a real pattern in the universe. But because it reminded me that patterns change, that the universe is always evolving, always exploring new configurations, and the configuration I was in right then wasn't permanent. Since then, I've tried to apply that to everything. When something good happens, I appreciate it fully, knowing it's a temporary pattern. When something bad happens, I remember that it's also temporary. Everything is just the universe trying out different arrangements of information, seeing what works, what creates more complexity, more integration, more consciousness. And we get to be part of that process. We get to experience it from the inside. We get to create new patterns, new possibilities that the universe has never explored before. That's what gives life meaning in an emergent universe. Not some external purpose handed down from on high, but the fact that we are the universe creating meaning for itself. We are the way complexity grows, consciousness expands, and understanding deepens. And here's my final question for you, the one I want you to think about after this video ends. If you really are a pattern in the universe's web of information, if your choices ripple through that web and influence the future in ways you can't fully predict, what pattern do you want to create? What ripples do you want to send? Because in a very real, physical sense, that's all any of us can do. We can choose what kind of patterns we are and how we interact with the patterns around us.
Let me wrap all of this up, because we've covered an enormous amount of ground. We started with a simple question: what if space and time aren't real? And we discovered that this isn't just philosophy, it's cutting-edge physics backed by mathematics, experiments, and observations. Space might emerge from quantum entanglement, from the pattern of correlations between different parts of the universe. Time might emerge from the direction that entropy increases, from the way information spreads and becomes more distributed. Gravity might emerge from the statistical behavior of information, from the universe's tendency to move toward higher entropy states. Everything we thought was fundamental, the bedrock of reality, turns out to be a pattern, an emergent phenomenon that only appears at certain scales. And the thing that might actually be fundamental is information, quantum information, relationships, correlations, and the rules that govern how they change. This completely changes our picture of reality. We're not objects in a container, we're patterns in a network. And everything from the smallest particle to the largest galaxy to consciousness itself is part of that network. The evidence for this comes from black holes, which store information on surfaces rather than in volumes, from quantum entanglement, which connects parts of the universe in ways that don't respect ordinary distance, from the holographic principle, which shows that entire dimensions can emerge from lower dimensional quantum descriptions, and from the Planck scale, where space and time themselves break down into something more fundamental. This isn't just academic, it has implications for technology, for consciousness, for the nature of meaning itself. We might be on the verge of learning to manipulate reality at the information level, to create new forms of consciousness, maybe even to preserve patterns that would otherwise dissolve. And on a personal level, it changes how you can think about yourself and your place in the universe. You're not a tiny speck in a vast void. You're a pattern in the universe's web of information. You're the way the universe has become aware of itself. And every choice you make, every connection you form, every thought you have creates ripples in that web that persist and influence the future. In a universe where everything is connected, where nothing exists in isolation, you matter. Not because some external force says so, but because you are the fabric. You are the universe experiencing itself, creating meaning for itself, exploring new possibilities. And that, to me, is both humbling and empowering. It's terrifying and beautiful at the same time. Space and time aren't what we thought they were, but reality is far more interesting than we ever imagined. We're living in a universe that creates itself from information, that builds complexity from simplicity, that generates consciousness from matter and energy. And we get to be part of that process. We get to witness it. We get to shape it. The stage you thought you were standing on doesn't exist, but the performance is real. And you're not just watching it, you're part of it. You're creating it with every moment of your existence. That's the dark truth about reality. It's not what it seems, but what it actually is so much more remarkable than the illusion could ever be. If your mind is completely blown right now, you need to watch my next video where we explore what happens to your consciousness when you die in a universe made of information.